Hello, everybody, and welcome to this episode of the Ampere Developer Impact. I'm joined today by Lars Wilkman of Underjord. I hope I got that pronunciation right, Lars, although I know you would pronounce it differently.
Right.
Do you want to give us the real Swedish pronunciation?
Lars Wilkman, and I run a small consultancy called Underjord.
Underjord. Okay, excuse me. I hope my second attempt didn't massacre the Swedish pronunciation.
It has an interesting mix of accents worked into it, but yeah.
Okay.
All good. I'm quite used to it.
So I'm joined today by Lars because you wrote a fairly fascinating blog post a little while ago describing how you used an AmpereOne 192 core server to boot 5,000 Erlang VMs. So this seemed like a massive oversubscription of the server to me. This is the title of the blog post: Booting 5,000 Erlangs on AmpereOne 192 core. We will include in the show notes so that people can go and read all the dirty details. But I wanted to talk to you, Lars, because, well, first, beyond the title jumping out at us, it seemed like a pretty unusual and interesting use case that you had. Could you describe exactly what you were trying to do and why the Ampere server that you use seemed like a good fit?
Yeah. The initial thing was just a fun idea, like how many, assuming we have this hardware, how many IoT devices could we run virtually on it? And then it turned out it might actually be useful as well. That was not the initial attempt, but we can touch on that. But the reason we ran 5,000 Erlangs, or eventually even 7,000, is because I work with an IoT framework called Nerves, which runs the Erlang virtual machine, which is very known for reliability and resilience, so that you can program embedded in IoT devices with Elixir, which runs on the Erlang VM, and it's a very nice, well-tooled, high-level language that is very suited to like networked applications and stuff. And kind of the path from just being told like, hey, actually, we could probably do something with an Ampere. This was in my conversation with Glesis, Swedish data center provider. And they were going to sponsor a conference that I organized. So that was sort of the reason we started discussing what they had on offer. And I talked through some stuff like, oh, GPUs, yada, yada, lots of regular servers. And he's like, you might be interested in this. Like, have you heard of Ampere? I'm like, yes, I have heard of Ampere. They have a lot of cores. I care about cores because I'm an Elixir developer. Elixir is very good at utilizing multi-core. I haven't benchmarked that as much as I would like on these Ampere ones. Maybe we get there someday. But I wanted to angle it towards like IoT and embedded Linux devices because I work with that day to day. I run an OTA service for updating IoT devices. So it would be an interesting demo of the stuff I work on day to day. It would potentially be useful to the Nerves project, and I'm a maintainer and open source developer on that project. And it would also be very interesting because a large part of the conference was people interested in Nerves. So that was kind of
the genesis.
Yeah, that was the core of the idea. Then it was like, how many of these could we stuff onto it? I know these cores are fairly fast, so we should be able to do more than one per core, was my initial thesis, and it kind of proved out.
Okay, so that sounds like a fascinating use case. Was there a particular reason why an ARM server was a good match here? Ampere creates ARM CPUs, right? ARM64 CPUs.
Yeah.
Is there a particular reason why ARM was a good fit there?
I probably wouldn't have gone into the IoT plan if it wasn't for the fact that I realized, oh, hold on, this is ARM, so we should probably be able to do this with good performance. So typically when you do embedded devices, like Nerves can run on x86, but typically when you're working with embedded devices, you're working with ARM devices. I guess RISC-V is also a thing now, more than it ever has, but it's still not really a thing. So lots of ARM in my day-to-day when I work with clients and so on.
Okay.
And that kind of brought me to thinking about this, like running multiple virtual devices. And then I started, of course, researching that and looking, we should be able to do KVM, so kernel virtual machine support, which should mean we get very little overhead for running ARM on ARM.
Right.
And not
and so
actually emulating, but virtualizing.
What were you actually virtualizing? You were virtualizing device images. Is that correct, or the OTA delivery mechanism? What actually gets run?
So what we built, we call it a nerve system, but it's essentially a very lean Linux build that starts the Erlang virtual machine. So it's a Linux kernel, it's a root file system, and a bootloader. And you can actually, when you're virtualizing, you can usually skip the bootloader, but in our case, we shouldn't, because that's how we track when we do updates, A/B partitions, and that kind of bookkeeping, and keep making it reliable and all that. So if we actually wanted to test nerves properly with virtual devices, we needed a bootloader as well.
Okay.
Yeah. So it's those three things is usually what you need to be able to start a virtual device. It's the rootfs, the kernel, and the bootloader.
But then what is the application that's running in the device? It's going to just copy a firmware to a device and verify that that device is correctly updated, or what is the application?
So it starts the full nerve system, which does a bunch of things, like keeping track of time, providing an SSH service if we want to, but it also connects then to Nerves Hub, which is another open source project for over-the-air updates. And so that's opening a WebSocket, keeping tabs on that, and whenever the server decides to push an update, it would update.
Okay.
So when I had many running, I was pretty sure it would be the nice demo, like giving an actual workload. And doing an OTA update is not the heaviest workload in the world, but it's also not entirely trivial, because there's a decent bit of like compression and encryption and signatures and stuff happening. So running a bunch of those seemed fun, and also for demo purposes, very, very effective when you can see the progress bars going out for many, many devices.
Okay. So one of the things that I really enjoyed in your blog post is that it's kind of a hero's journey. You chart how you start with, was it 300 was your first attempt, was to try with 300 before you started?
I made the first post at 500.
500.
Yeah.
So you started with 500 VMs. Can you talk through some of the ways that you got from 500 to 5,000? And I know in particular, like oversubscribing the CPU to that extent and oversubscribing memory to that extent. Those were the two things that really jumped out at me. And also you mentioned the bootloader, not bootloader, bootloader. You built your own bootloader?
We built our own bootloader. I can't take very much credit for it. I helped debug a bootloader a little bit. So the creator of Nerves, the original instigator of the project, Frank Hunleth, like he's done so many U-boot implementations. So U-boot is a typical bootloader you'd use for these types of things, that apparently that was kind of dull for him. But I had asked him to bail me out if I got stuck on the bootloader, because I knew the bootloader would be tricky for me. I haven't worked that much, particular with bootloaders. And so during this process, he shows up and goes, "Hey, me and ChatGPT figured something out." And then he throws me a bootloader called Little Loader, and we iterate on that. And it's a very, very simple bootloader. So it's actually a pretty good, if you want to try and understand both ARM and QEMU, it's a pretty good sort of sample project. And it's also just a good sample project if you want to look at how bootloaders might work, how they can work.
Okay.
Because it's a fairly lean and simple bootloader. It does a few nerve specific things. It's very sort of directed, but it doesn't do anything particularly odd. I'm not super experienced at reading C, and I could still follow it.
Okay.
So,
so what were your first steps when you mentioned QEMU or QEMU as that's the user space component of KVM, right? That's what basically is the thread running the virtual machine.
Yeah.
What were the first things that you did to be able to kind of oversubscribe memory and CPU using QEMU with KVM in the backend?
Yeah. So the first approach was just trying the simplest things, just looking up like the commands that, well, the build root builds, because Nerves builds on top of build root for building the Linux and all that. So setting up a build root build that would set up QEMU and run on this machine, and just tried that. And initially we had some issues with our nice new bootloader that it wouldn't do KVM. So my first attempts were straight up emulation. So we just told it to act like you're an A53 core or whatever.
Okay.
And that's when I just went, okay, it runs. So let me see how many I can do. And it did 500 without much issue. Each VM was taking about 660 megs of RAM. And I had the expectation that we could get them down to about 120 because I've seen that before.
Right. That's just by stripping pieces of the application operating system out?
Yeah, I would have expected these to be
OS.
between 120 and 200 because it's a fairly lean setup already.
Okay.
But it was at 660 looking from the host side. So QEMU was taking 660-ish.
Got it.
And the moment we got KVM working, that dropped to 220 or something. Or even maybe 150. I don't recall exactly.
Right.
But the moment we could do KVM, it just removed this whole need to emulate a CPU, right? Which apparently takes some RAM to do. It also sped up the boot sequence by, I didn't feel like it was slow, but maybe it took 10 seconds or something earlier, and now it took like 2 or something.
Okay.
But that's also when I started cranking out more VMs. So the moment I had released my 500 VMs blog post, we fixed that thing, and then I could do 3,000 without issue.
Okay. Let's talk a little bit about kernel same page merging, which was kind of one of the big superpower boosters for this platform. Yeah. So can you describe what it is and how it fit into the picture?
Yeah. Because we started looking at ways to constrain the memory usage. And we could do some things within each guest, like we did RAM compression and a few different things, tune the allocators and dirty pages and all that. But it felt like there was some stuff that could be done on the host, because every kernel and every rootfs is identical. And it felt like there was something we could do there. So I looked around a bit and found kernel same page merging, which is just a mechanism that lets the system go through memory pages and figure out duplicate memory pages and just merge them until they diverge, I suppose.
Okay.
Ours very rarely diverge. They could change a little bit when you push like a firmware update, for example, but overall our pages are very, very immutable, most of them, because the root file systems are immutable. We don't store a bunch of logs on the disk or anything. So almost no changes. And typically you run this to reclaim memory when there's memory pressure. So the default configs was almost useless to us because, well, it was slow because it would wait until there's pressure and then reclaim pages. And then, so I ended up configuring it to just run constantly, aggressively, grabbing a lot of pages and looking through them. And over time, just by waiting and starting more VMs after a while, waiting a bit, starting more VMs, like it kept reclaiming memory and I kept being able to start more VMs. 5,000 at the point at that I wrote the blog post. Personal best was 7,000, and then I actually had to back off because my co-founder of NervesCloud, the hosted version of Nerves Hub that we run, was like, "Hey, we're seeing some scaling issues over in California." I believe I was running this on some hardware I got from you all, at that time. Later, we moved it over to Glesis in Sweden when they got what I think is maybe, I don't know if it's Europe's, but it's probably Sweden's first AmpereOne. So when they got set up, we ran it from there as well. But I didn't push too far. It's like there's some bottlenecks that's probably on our cloud provider that I didn't want to spend time debugging while I was doing this. So that was actually the reason I had to back off. Though I will say, when I started going to a couple of multiple thousands of devices, 5,000 was fine. But occasionally you'd see a VM go unaccounted for in my little demo app. And I think that is essentially just
out of memory
bad fortunes in timing, because occasionally it gets very intense on the machine.
Okay.
And if that times out for whatever reason, that kind of thing. I've seen a few quirks like that I haven't dug deep on.
So we haven't talked. We've talked about memory pressure and oversubscribing memory, but we didn't talk about how much memory you had and how much virtual memory you ended up using across your 5,000 or 7,000 VMs. So how much memory was in the machine?
1 terabyte, which is
only 1 terabyte.
Yeah, it was a cheap old machine, very limited. They kept telling me 4 terabytes is very, very pricey, and like, I don't know, I don't get the price tags on this. I just got to borrow the machine. No, I'm very happy with the terabyte, and I think it was also a decent constraint to work against.
Okay. So 1 terabyte divided by 5,000, that's 200 megabytes per VM, right? Were you using 200 megabytes virtual memory per VM, or with KSM, like, how much virtual memory was each VM showing?
So it doesn't show up as virtual memory as such. I could see how much I had reclaimed, essentially. And when I filled it up at around 7,000, I believe I had reclaimed 400 gigs of memory. But it was still counting, so...
Right. Okay.
But essentially, it could reclaim a ton. We could probably oversubscribe more than double in theory. In practice, I'm not convinced. But and at some point, CPU contention becomes a thing.
Okay.
But I didn't really reach that point.
Right.
In theory, these devices, like, I think it's at 5,000, or it might be at 7,000. But I did the math at some point, and I don't think it splits this evenly, but every device essentially had 69 megahertz.
Right.
But of course, it has a 69 megahertz share, but it could potentially boost to the full, what is it, 3.2 gigahertz?
The AmpereOne has 3 gigahertz to 3.5 gigahertz cores. I'm not sure what yours was set at. And so you end up with each with, let's round to 200 cores with 7,000 VMs. That's 35 processes running simultaneously per CPU, and they're all getting a slice of the CPU plus all of the housekeeping that goes on in the operating system, right? So okay.
We showed the CPU usage of the entire machine when we were starting, like, let's start 1,000 VMs and see what that does. The first demo being, let's start 1 VM and see what that looks like.
Right.
And we had just visualized the 192 cores in color. And then, like, okay, 1 core turns orange for a split second, and then it's calm. Like 10, okay, you can actually see that it's like, a few dots of orange and maybe 1 red. Then it's like 100. Okay, now it's a bit of a Christmas tree because it's a lot of mixed colors. And then you hit 1,000, it's just red for a while. And the load average just skyrockets because you're starting so many things at the same time.
Right.
But
it can take it.
Yeah. I have hit this thing with starting 5,000 VMs essentially immediately. And I mean, load average will shoot to 500, 700, but eventually it calms down and just hums along. So it's been very, very reliable and very stable. I haven't had a weird issue during the entire time.
Right. So thank you very much, Lars. To summarize what we've talked about, so Elixir is a functional language that runs on the Erlang VM which is itself Erlang as a functional language from the 1980s, which comes from telco world. And you were able to push a 192 core AmpereOne system to run up to 7,000 parallel QEMU threads, so 7,000 parallel virtual machines on a single host, oversubscribing both memory and CPU quite intensely, I will say, and to run an over-the-air update of up to 7,000 embedded devices at once. Does that summarize everything we talked about so far?
Yeah, pretty much. Yeah.
Well, thank you very much. This is a wonderful use case, and it's a wonderful example of how somebody can use a lot of cores when they're available.
Yeah.
And thank you for writing your blog posts. They've been wonderful reads, and I really enjoyed going down the rabbit hole of things like your own bootloader and KSM tuning. And thank you very much for joining me.
It was a lot of fun. Thank you for having me.
You're most welcome. It's been my pleasure. And thank you, everybody, for watching. And we will see you soon on a future episode of the Ampere Developer Impact.